Okay, wonderful. Well, thank you very much. I want to thank Evelyn and the organizers for putting this together and for inviting me to speak at this session. So I'm going to be talking about structure preserving integrators for what I'm going to call Hodgkin-Huxley type systems. And this is going to include the Hodgkin-Huxley model for neuronal dynamics, as well as some other types of systems. Like the earlier talk, I'm actually going to be talking quite a bit about splitting methods and their ability to preserve spiking dynamics. So this is joint work with my two co-authors, Zhengdao Chen, who was a really remarkable undergraduate at Washington University, who's now doing his PhD at Courant at NYU, and Bharani Raman, who is a systems neuroscientist in the biomedical engineering department at Washington University. So, so the motivation comes from these Hodgkin-Huxley equations for neuronal dynamics. So here we have the equations for a neuron where V corresponds to the voltage, I is an input current, and these N, M, and H are gating variables corresponding to ion channels. And the idea, as I'm sure most people know here, since this is about mathematical neuroscience, is that for low currents, the system sort of stays at a resting voltage. However, when the input current increases beyond a threshold, a dynamical bifurcation occurs. And as a result, the voltage begins spiking periodically. And this is how neurons send out action potentials. So here I have a picture of sort of what this looks like in time. I've turned on the current here, and you see there's one large initial spike and then repeated spikes after that, and then the current is turned off and there's no more spiking. And if we look at this in phase space, I'm only going to show really most of the interesting dynamics happens in 2 dimensions. We can look just at N and V. We see that we start at this fixed point here, but when the voltage increases, the system is attracted to this limit cycle, which corresponds to this periodic orbit that corresponds to the spiking behavior. So this is an example of what's called a relaxation oscillator. So although it's undergoing periodic motion, this is not like a pendulum or a spring mass system. The periodic behavior doesn't come from conservative or Hamiltonian dynamics. It actually comes from dissipation. This term, relaxation oscillator, goes back to van der Pol, who described it that way in 1926. And as I mentioned, it describes nonlinear dynamical systems that, although they feature dissipation, they have dynamics that resemble conservative systems, for example, periodic oscillations. And this results from an interesting interplay between the fast and slow time scales of the dynamics. So as was discussed earlier with Fitzhugh-Nagumo, we would like to, for reasons of computational efficiency, simulate these equations using explicit numerical integrators with large time steps. Of course, these are nonlinear dynamics, so we can't solve them exactly. We need to do computation, and this will minimize the expense of our computation and allow us to get sort of efficient results. So there are basically 2 obstacles to taking large time step sizes when using an explicit numerical integrator. One is numerical stability in the presence of stiffness. So if you have a very stiff system with strong damping or oscillation, if you take a time step that is too large, then it blows up and becomes numerically unstable. So that's a problem. And on the other hand, you have the question of preserving limit cycles that correspond to these oscillations. These limit cycles describe the dynamics that we're interested in, which is the spiking of neurons. So even if our method is stable, if we don't get this limit cycle right in our numerical method, we will not get meaningful results. So in practice, it seems that a lot of previous work on numerical methods for Hodgkin-Huxley and other models of neuronal dynamics has focused on this first problem, the question of how can we get a method that's stable for large time steps. But this second question has not, I think, received quite as much attention. So I'm going to talk a little bit about that. And in practice, this second consideration is much more restrictive. And for some of the methods people have described that are stable for large time steps, even though they're stable, they require much, much smaller time steps in order to get the limit cycles correct. So in practice, they really do require time steps that are much smaller than their stability criteria would indicate. All right, so the results that we show are that what we call Euler-type methods, which are methods similar to Euler's method itself, as well as some stabilized exponential and semi-implicit versions of Euler's method. Even if they're stable, they do not accurately preserve these limit cycles at large time step sizes. So in practice, they require time step sizes to be just as small, even for these stabilized versions, as the traditional Euler method. And we're going to discuss other methods that do preserve these well, or better than the Euler-type methods. And these are, to sort of give away the punchline, are going to be splitting methods. So to motivate, so I kind of come from, I don't come from a background in mathematical neuroscience. I come from an area of numerical analysis that's concerned with numerical methods for systems with some geometric structure, such as conservative or Hamiltonian systems. So here's a simple example of one. If we have the simple harmonic oscillator, we can describe it by this Hamiltonian, which is just 1/2 x1 squared plus x2 squared in phase space. Right? And if we write down Hamilton's equations, this is just the first order form of the simple harmonic oscillator, written in terms of, we can think of x1 as displacement and x2 as velocity. So this is actually an example of something that's called an integrable system, right? Phase space is the plane, and it's completely filled up with the orbits, which are just circles. So if I start on one circle, in phase space, my oscillation is just going to look like going around this circle. And we can describe this behavior by changing to what are called action and angle variables. So the action is just this Hamiltonian, or the energy in the system. And the angle is just the phase angle in the phase plane. And in these variables, we can see that the action does not change at all because energy is conserved. And basically, all the dynamics are happening as this phase, as the system oscillates, the phase angle is changing at a constant rate. All right, so in phase space, solutions are just winding around these invariant tori, as they're called. Really, they're tori in higher dimension. In this case, they're just circles with constant angular velocity. All right, so the van der Pol oscillator, which was of course, introduced by van der Pol and is the basis for some models of some neuron models, including the Fitzhugh-Nagumo model, starts by taking the simple harmonic oscillator and adding this term with epsilon. So we add some nonlinear dissipation where this dissipation parameter is epsilon. So when epsilon equals 0, it's just the simple harmonic oscillator. So when epsilon is very small, we can show that this has a fixed point at the origin and a limit cycle with radius approximately 2. So when epsilon is equal to 0, we have all of these invariant tori. We have the whole plane filled with concentric circles. However, when we move epsilon away from 0, all of these disappear with the exception of the one with radius 0 and one with radius approximately 2, which is this limit cycle. So here we see an example of a solution sort of spiraling out and ending up on this limit cycle with a radius approximately 2. So the way that van der Pol analyzed this behavior, why is it the case that we have this fixed point at 0 and this limit cycle with a radius approximately 2? Well, we can take the van der Pol equations and transform them into these action angle variables, a and theta. Right? And now we no longer have a dot is equal to 0. A dot is this expression involving epsilon. And we have this expression for theta dot. And when epsilon is very small, right, we can see that the variable a changes much more slowly. It changes on the order of epsilon, where this is O of 1. So basically, we can, since the angle is changing so much more quickly than the amplitude, we can average over all the angles between 0 and 2 pi, and we get this equation for the average dynamics. So the average dynamics, we see that theta dot is asymptotic to -1. And if we look at these dynamics for how the amplitude changes, we see that there are two fixed points, one at a equals 0 and one at a equals 2. And that's the reason for this fixed point at 0 and this limit cycle with approximate radius 2. All right, so when epsilon is negative, the fixed point is stable and the limit cycle is unstable. However, if we increase epsilon past 0, there's a Hopf bifurcation and then the fixed point becomes unstable. So much like a neuron, right, this thing will stay at a fixed point, but when we increase the parameter enough, all of a sudden the fixed point becomes unstable and it jumps to the limit cycle and begins oscillating. So when epsilon is much greater than 1, so when epsilon is large, there's also a similar limit cycle spiking type behavior, but it's not as well described by this method of averaging. We can change variables using this thing called the Liénard transformation, which I'm calling y1, y2 instead of x1, x2. In terms of these variables, and this is more closely related to how the Fitzhugh-Nagumo model is typically written. All right, we have this cubic null line here, and we see that the dynamics of y1, if epsilon is large, are very fast. Dynamics of y2 are very slow. So what happens is the solution jumps between branches of this null line and then crawls slowly along it, then jumps again, right, and so on and so forth, and we get this spiking behavior. All right, so what do the van der Pol oscillator and Hodgkin-Huxley have in common? Well, one thing that they have in common, as we've seen, is they both feature these sort of bifurcation and limit cycle dynamics. But another thing that they have in common is that they're what is called conditionally linear. And what that means is that although they are nonlinear, right, if I freeze all of the other variables and I look at just one variable, that actually satisfies a linear equation with constant coefficients. So here, for example, if I look at x2, this is a nonlinear equation. However, it's only nonlinear in the other variable x1. And if I were to freeze x1, then x2 satisfies a linear ODE, and similarly for x1. With the Hodgkin-Huxley equations, right, if I freeze n, m, and h, then v satisfies a linear equation. And similarly, if I freeze v, then n, m, and h satisfy a linear equation. So there is nonlinearity, but it's sort of a milder form of nonlinearity, where the nonlinear part is only the other variables, other than that particular one that we're looking at. Okay, so how are we going to approach this? Well, the goal is going to be to integrate systems like this with as few evaluations of the nonlinear functions as possible, because these typically dominate the cost of numerical integration. And as I mentioned, we use this observation that if I freeze all the other variables with j not equal to I, then xi satisfies a linear ODE with constant coefficients. Right? And we can solve linear ODEs with constant coefficients exactly. So if I use this to mean the time h flow of xi, where all of the other xj's are held fixed, then this is how xi evolves, right? It evolves like this, and xj stay the same. And we can do this more generally. We don't have to do the exact flow necessarily. We can use an approximate flow, for example, coming from, right, I could apply some Runge-Kutta method to this system. And even if it's an implicit Runge-Kutta method, if I freeze all the xj's with j not equal to I can come up with an explicit formula for a solution. All right, so I say that an Euler-type method for a conditionally linear system has the following form, meaning that for each of the xi's, I just apply some numerical method to the previous time step, right? And I do this sort of stepping forward in parallel because each of the xi's only depend on the state of the system at time n. All right, so this includes Euler's method, the exponential Euler method, as well as the semi-implicit Euler method, which is sort of is related to basically applying backward Euler to that frozen system. Okay, so Euler's method is well known to have problems with stability in the presence of stiffness, but the exponential and semi-implicit Euler methods are much more stable, and for this reason they've been proposed as good methods for the Hodgkin-Huxley equations due to these stability properties. On the other hand, as opposed to Euler-type methods, we can also look at splitting methods or composition methods. And the idea is that rather than stepping forward each of the components in parallel, we do it in series. So I would step x1 forward, then x2, then x3, right? Go down, and if I were doing this symmetric composition, I would then go back in the opposite order the next time. All right, so examples include the Sturmer-Verlet method, also known as the leapfrog method, which is a symplectic integrator that's widely used for Hamiltonian systems, as well as the Strang splitting method that was mentioned earlier. So for the van der Pol oscillator, we actually see that the splitting and Sturmer-Verlet methods do a very good job of maintaining this limit cycle with radius approximately 2. However, the exponential and SI Euler methods give distorted limit cycles that have radius much too large, right? And this is a theorem that appears in our paper that explains this. Basically, splitting or composition methods have limit cycle radius that's that has an error O of h squared independent of epsilon. However, Euler-type methods, you have this dependence of the radius on epsilon. So when epsilon is very small, you get a distortion in the limit cycle radius. And that means that effectively we require h to be not just smaller than 1, but in fact much smaller than epsilon, which is much more restrictive than the stability criteria. And so this can be described via backward error analysis. We think of the numerical flow as being asymptotically the flow of a modified vector field. And you can show that the modified vector field for Euler-type methods has these additional terms. And when we do the method of averaging, we pick up this error in the limit cycle radius. On the other hand, for splitting methods, we can use the Baker-Campbell-Hausdorff formula to get the average dynamics and show that the limit cycle is 2 plus O of h to whatever the order of the method is. So here are some further numerical experiments with the non-stiff van der Pol oscillator. Again, we can see that as the time step size increases, right? So for very small time step sizes, all the methods do well. For larger time step sizes, we see these Euler-type methods have an expanding limit cycle radius. And this even happens for a higher order method, the exponential midpoint method. We see for this large time step, the radius is a bit too large, and the system is being attracted to the limit cycle too quickly. Whereas these splitting and composition methods do a good job of preserving the correct limit cycle behavior. We also see something similar for the van der Pol oscillator. We see that the splitting and Sturmer-Verlet method do a good job of preserving this limit cycle that jumps between the branches of the cubic nullcline, whereas we see this distortion for the Euler-type methods that results in a decrease in the frequency and increase in the amplitude of oscillations. So here are some further numerical experiments, and it appears that, so interestingly, although right, we do get some distortion with the symplectic Euler and Sturmer-Verlet method, the Lee-Trotter and Strang methods actually do quite well. Even though this one has some distortion, it actually, the distortion is only in the jumping part of the limit cycle where the solution spends very little time. So in fact, we see that it correctly captures the amplitude and frequency of spiking quite well. Right, so we see this in this picture. So here we see that Lee-Trotter and Strang, the basically spiking behavior in time looks the same as we take the time steps larger. With the Euler-type methods, we have this decrease in frequency and increase in amplitude. And we also see some distortion for the exponential midpoint, symplectic Euler, and Sturmer-Verlet methods. So the splitting methods seem to do the best of all when applied to either the non-stiff or stiff van der Pol oscillator. So we can do the same thing with the Hodgkin-Huxley neuron, and we observe something similar. So we see that the splitting method tends to, with the same numerical experiment I showed before, get approximately the right spiking frequency and amplitude. The exponential Euler and SI Euler methods, we see, again, a decrease in spiking frequency. And as a result, right, whereas these three methods, whereas the reference in these two methods fire the correct number of spikes, exponential Euler and SI Euler fire fewer spikes in the time between when the current is turned on and when it's turned off. And that's due, we can see, to sort of limit cycle distortion, where it takes too long to get around these periodic orbits due to the distortion of the orbits in phase space. Right, so here are some further numerical experiments. Again, we can see this distortion in phase space, which is more severe, especially you can see for the SI Euler method. This loop is really sort of shrunk over here. And we can also see it in terms of the time variables, where here, for example, this is 0.4 milliseconds. The exponential Euler and SI Euler method have each lost some spikes. So this is 6 spikes, this is 5 spikes. The exponential midpoint even gives only 6. We've lost 1 here, whereas Lee-Trotter and Strang splitting give the correct number, 7 spikes. And you only start to see breakdown at a larger time step than you see for these other methods. All right, so to conclude, efficient numerical integration of relaxation oscillators require explicit methods that not only remain stable, but also preserve limit cycles for large step sizes. If we're interested in spiking dynamics, we should be concerned not only with stability, but limit cycles. Splitting and composition methods are better at preserving these than Euler-type methods without sacrificing stability or computational efficiency. All of these methods, right, the Strang splitting method, like Euler's method, only requires 1 evaluation of each nonlinear force per step. So it's exactly the same computational expense, essentially, and you really get this better behavior without having to do additional computation. We have some theorems that explain this for the non-stiff van der Pol oscillator. But we don't yet have one for the stiff van der Pol oscillator or Hodgkin-Huxley. We only observe these things through numerical experiments. And of all the methods we considered, the symmetric or Strang splitting method seems to have the best combination of stability and limit cycle preservation. All right, that is it. And thank you very much for your attention.
Thank you very much for this interesting talk. Thank you. There do not seem to be any questions at the moment. Oh, there are.
Probably I have a question.
Yes.
Really?
This one first.
Yes, okay.
Robert Gowers is asking, how is spike timing affected by the choice of numerical method? For example, the time of the first spike after an applied current input.
Oh, how is spike time affected by the choice of numerical method? Generally, we saw that, so let me go back to this here. So generally, we saw that for small time steps, all the methods do quite well. Although here, even SI Euler, we're seeing fewer spikes. Generally, the spikes, as we increase the time step size, the spikes become farther apart. So it'll take a long, right? So here, for example, the fifth spike arrives around I don't know, 120 milliseconds, whereas here it's closer to 150 milliseconds. And we see that with the exponential Euler and SI Euler methods, this this delay between spikes increases more quickly with time step size, whereas it still happens even with the splitting methods, but the sort of the stretching out of the spikes happens more slowly, right? And it only becomes severe at larger time steps.
Okay, thank you. Wilhelm, what did you want to?
Oh, I think you're muted.
You're muted.
Sorry, have you looked at networks? I mean, the same splitting method for, let's say, structure preserving dynamics on networks?
Yeah, no, that's a great question. So we started by looking at the single neuron dynamics, and looking at networks is ongoing work. I don't have any results to report on that yet. But that's certainly the next step.
Okay, thank you. And I think I switch you off.